today we are going to be working with Pythagorean Theorem. Pythagorean Theorem applies to right triangles, and we will be using Pythagorean Theorem many different times throughout this year in geometry, including something that is coming up yet in this unit, which is why we're going to talk about Pythagorean Theorem, and also why we looked at simplifying radicals in our lesson yesterday, reviewing that information. So again, Pythagorean Theorem works for right triangles, and what it does is allows you to find a missing length of one of the sides of the triangle if you have the other two sides. Key thing in this Pythagorean theorem, which is given to us as c squared equals a squared plus b squared, is correctly identifying the c. Okay? That c is the hypotenuse of the right triangle, which is the side opposite of that right angle. The other two sides of that right triangle are called the legs, and it doesn't matter which leg you put in for A and which leg you put in for B. Most important thing, again, is to make sure that you correctly identify that hypotenuse, because that term squared goes by itself on one side of the equation. The two legs squared goes on the other side. So this Pythagorean theorem is what we are going to be working with today. We're going to look at several different examples. First, we're going to look at some examples where C is unknown. Up here on the overhead, I have pictures of triangles. You can either draw in the picture in your notes and label the sides as you see up here, or you could just write down A equals 3, B equals 4, C equals question mark, and then show the work that we're going to go through. So in this first triangle, they've identified the three sides for us. So I'm ready to plug that information into Pythagorean theorem. So c squared equals 3 squared plus 4 squared. Now I am ready to simplify that. So on the right side, 3 squared is 9, 4 squared is 16, 9 plus 16 is 25. So c squared equals 25. But I'm not looking for c squared. I'm looking for c. So when we're solving equations, guys, quiet and listen, please. When we're solving equations, we undo or work with the inverse operation to undo things. So I have this term squared that I want to go away. What do you think the inverse operation of squaring something is?
Dividing it?
Not dividing. We want to make it smaller. What's the square root? So what I have to do is take the square root of both sides. Okay? The square root and the square, the exponent of 2, are inverse operations. They get rid of each other, so I'm just left with that variable c. There's no exponent, there's no square root symbol anymore. Just the letter c. On the right-hand side, what is the square root of 25? 5. And that's my answer. Next one. Again, we're looking for C. As I mentioned before, it doesn't matter which side we call A and which side we call B. So C squared equals 4 squared plus 6 squared. And then again, we do the math. 4 squared is 16. 6 squared is 36. Added together, 52. So C squared is 52. But again, I don't want C squared, I want C. So I'm going to take the square root of both sides. Square root of C squared is just C. Square root of 52, is 52 a perfect square? No, it is not. So I need to simplify the radical, which is what we reviewed yesterday. Okay, do we want to do the perfect square method or the factor tree? Okay, I heard both. I can show both. Okay, if we're going to do perfect squares, what's a perfect square that goes into 52?
What?
7 doesn't go into 52, and 7's not a perfect square. 6 is not a perfect square. 8's not a perfect square. 4 is a perfect square. If you want to use a perfect square method, you have to know your perfect squares. Okay, 4 is a perfect square. 4 times what is 52?
12, 6, 13.
4 times 13 is 52. The square root of 4 is what? 2. Square root of 13. Is there a perfect square that goes into 13? No. So 2 square root of 13 is the answer. If I'm going to do the factor tree, what are any two factors of 52? 4 and 13. Factors of 4? 2 and 2. So I'm looking for pairs. I've got a pair of 2's. So a 2 comes outside. The 13 stays inside. So either way, I get that same answer of 2 square root of 13.
Wow.
In the next two examples, this time I know the hypotenuse. I'm looking for one of the legs. So when I plug that in, C is 14. So 14 squared equals A squared plus 10 squared. So I do the math. 14 squared is 196 equals A squared plus 10 squared is 100. So this time I need to subtract 100 from both sides. So 96 equals A squared. But again, I don't want A squared, so I take the square root of both sides. Is 96 a perfect square? No, it is not. What's a perfect square that goes into 96?
4.
4 goes in. How many times does 4 go into 96?
27.
20,
It's 24.
24. Okay. Square root of 4 is how much? 2. Is there a perfect square that goes into 24? 4. So we have to go again. Square root of 4 times square root of 4 times what is 24? 6. So again, square root of 4 is 2. Is there a perfect square that goes into 6?
No.
So 4 square root of 6
That's special.
is the answer. If we're going to use a factor tree instead, any two factors of 96.
8 and 12.
8 and 12. What can I do to factor 8?
4 and 2.
4 and 2. What can I do to factor 4?
2 and 2.
2 and 2. What can I do to factor 12?
6 and 2.
6 and 2. What can I do to factor 6?
2 and 3.
2 and 3. So I've got lots of numbers here. So I have one pair and another pair. So 2 2s that come outside. These other 2 have to stay inside. So I get 4 square root of 6. Same answer, different method. Yes, Grace?
Are we gonna have to use this, like, be able to use both methods on, like, the test?
No, you need to use whichever method works best for you. Okay? Whatever method works best for you. Last one. This one. Okay? We need to, again, make sure we identify C correctly. Opposite the 90-degree angle. So 13 is the C. So 13 squared equals 12 squared plus y squared. I do the math. 13 squared is 169. 12 squared is 144 plus y squared. So I subtract 144 from both sides to get 25. So y squared equals 25. I need to take the square root, of both sides. What's the square root of 25? 5. And there is our answer. Want to talk about one other thing. You will see some of this in your assignment. What if instead of having this side length of 12, it was the square root of 12 instead of the integer 12? When I plug that into Pythagorean Theorem, I would have 13 squared equals square root of 12 squared plus b squared. So then I would do the math. 13 squared was that 169. What would happen here when I have square root of 12 squared?
Down, and once you get to your smallest number, you would multiply that or square root them or whatever.
Or would you do this for 12 and then just 12?
Okay. What did we say happens if we have a square root and a square?
They cancel each other
They cancel each other out.
out.
Just like with the y squared, the square root and the square cancel each other out. Just left us with the y. So if the square root and square cancel each other out, we're left with the 12.
Well, but don't you need the 144?
No, we're doing a different problem. We're doing square root of 12 instead of the integer 12. Okay, we were looking at what happens when you have a square root in your side length. Okay, So then you'd finish it out the same way. Okay? So knowing that saves you a lot of work, because otherwise, okay, if you squared it first, 12 squared is what? 144. What's the square root of 144? 12. So you're back to that number that was inside. If you did the square root first, okay, we would have 2 square root of 3. And if we took 2 square root of 3 and squared it, then we would get 12. So we'd be right back where we started. Okay, so just like with the variable, the square root and the exponent of 2 squaring are inverse operations. They undo each other. So we're just left then with what was inside of that radical. Okay, so again, you will see some of those on your homework assignment.